Hello, everybody. Welcome to today's lecture. So today we're going to start on chapter 12. This chapter is all about what's called linear regression. It basically is exploring the relationship between, in our case, two variables. Okay, so we have two things, and we want to know if they're related or not. More precisely, we're going to find out if they're what we call correlated. Okay. Um, So I talked about how chapter 9 was very important, and it is. It's maybe the most important chapter, but if not, then this is the most important chapter. Okay, these just this one and chapter 9 are both very important chapters. Um, Chapter 9 because you're often testing a hypothesis, but in chapter 12 you often are trying to determine if there's a relationship between two things. Um, just well, let's look at um some of the stuff in this first chapter here. Um, you might notice in the introduction, it talks about how um, we're only going to be looking at if there is specifically a linear relationship between two variables. But there are many different types of regression. There's what's called multivariate regression, where you're looking at multiple variables, not just one. And there's other types of regression that aren't even necessarily linear. Like there's quadratic regression, where you look to see if there's a quadratic relationship, or logistic regression, where you look to see if there's a logistic relationship. We're specifically going to be looking at if there's a linear relationship, meaning that if we were to graph their relationship, it would look like a straight line. Okay. So for that reason, we're going to be using a lot of stuff from college algebra. So if you've taken that class, that will really help you here. But I'm not going to expect that you have. Okay. So just starting on 12.1, okay, linear regression. Um, Linear regression for two variables is based on a linear equation with one independent variable. Okay. So typically you might hear it just referred to as linear regression with one variable. That's because that one variable they're referring to is the independent variable. There's two variables total, the independent and the dependent variable. So the independent variable is typically the variable we're choosing, and the dependent variable is the outputs, the ones that we don't choose, that just come out of the equation. On a graph, the independent variable is typically the x-axis, the horizontal one, and the dependent variable is the y-axis, or the vertical one. So the equation here has the form y equals a plus bx. Okay. Or you might know this as y equals mx plus b. Okay. So the letters we're choosing, the a or the b or the m and the b, are pretty arbitrary. But it's important to note that it's used differently in statistics than you might have seen it in college algebra if you took that class, where you see the y equals mx plus b. If you recall, m is the slope and b is the y-intercept. So in the equation up above, the b is the slope and the a is the y-intercept, because the slope is the thing on the variable, on the independent variable, and the y-intercept is the thing by itself. So those are going to have different meanings for us than we're used to seeing. Okay. So if it has this form, then it is a linear equation. If it doesn't, then it's not a linear equation. Where a and b are going to be known numbers. Okay. So a, b are just numbers. Okay. Which we would typically call constants. And then x and y are variables. Okay. Specifically x x is the independent variable and y is the dependent variable. So they're called linear because when you graph them, you get a straight line. Okay. Let's look at how we would graph them. Okay. What if we had something like y equals 2x plus 1? Okay. Okay, so I won't actually ask you to make these graphs necessarily, but I just want to kind of show you how to do this just so you're aware. So like I said, the x-axis is typically the horizontal axis and the y-axis is the vertical one. Okay. And it's really no different than the way we make graphs based on our data. We look at the x points and the corresponding y points, and we make a dot where they meet. Okay. The only difference here is that we don't really have any data, so we just pick the x's. Okay. So we can make a little chart over here, and we can look and say, okay, let's let x be 0, 1, 2, etc. Okay, you can pick the x's to be whatever you want because we don't have any data right now. And then we look at our equation and say, okay, if x is 0, then y is going to be 2 times 0 plus 1, which is 1. Right? So when x is 0, y is 1. So this would be 0, and then this would be y being 1. Okay. So let me label these. Now when x is 1, y is going to be 2 times 1 plus 1, which is 3. Okay. So when x is 1, y is 3. And we really can stop there. We don't really need this one because we know that, based on what we're doing, that this is going to be a straight line. And once you have 2 points, there's only one straight line you can make through them. Okay. So I didn't draw the rest of the graph, but we can use all of it here. If you just keep going this way, you have negative numbers. Okay. I'm used to just drawing the first quadrant, just this part for us, because we're usually dealing with positive numbers, but technically you can have negative as well. So if we have a different type of graph, like if we have something like, this, like this is something you might have seen recently with like the COVID numbers, right? You see that they're, if you look over time, they're kind of level, but then they start getting big like this pretty quickly, right? And this is an example of what we call an exponential graph. So there's no linear relationship, they'd have an exponential relationship. Or you could have something more like this. Again, it's not a straight line, so it's not a linear relationship. This is what would be called a quadratic relationship. Okay. So there's lots of different relationships, but if we see types of graphs like this, then we can't do anything with it because we're only looking at linear relationships right now. Okay. So with the y equals a plus bx, b is the slope and a is the y-intercept. Okay. Or if you're using the y equals mx plus b, m is the slope, b is the y-intercept. Okay. I'm just going to use this notation because it's consistent with the book, but feel free to use whichever one you want. So the y-intercept, I'll abbreviate it as y-int, is the place where the line crosses the y-axis. Okay. In other words, x is 0. Okay. If you're on the y-axis, on this axis, that means that x hasn't moved, so your x is 0. So in this case, it was 1, which we can see from our equation. It's the number that's by itself, just like a is the number that's by itself. The slope is the number of units y changes per 1 unit change in x. So as you move over x, as you move over once with x, how much did y change? Okay. So like here, if we're looking at going from 0 to 1, that's changing by 1 on x, right? You're going from 0 to 1, so you've moved 1. Well, in that transition, how much did y move? Y moved from 1 to 3, which is a difference of 2. So the slope here is 2, which we can see because that's the number that's in front of x. Okay. So that's just if we look at like one more equation here, I guess, if we have y equals -1 plus 1/2 x, okay, or we'll often be using decimals with this stuff, so let's say 0.5x, okay. That means our y-intercept is at -1, so we're going to cross the graph at -1, and every time x changes by 1, y is going to change by 0.5. Okay. So we got this graph here. So we start at -1 on the y-axis. That's when x is 0. Now as x goes over to 1, y is going up by a half. So it's going to be at about right here. We don't have to have it exactly, but it's going to go from -1 to -1/2. Now as x goes over 1 again, over to 2, y is going up another half. So it's going to be at 0, etc. And then it's just going to keep continuing like that. Okay. So I didn't draw it perfectly, but it should be a straight line there. All right. So this is just kind of the basics of what we're pulling from algebra. Now we want to look at 2.2 here, which is about scatter plots. Okay. So oftentimes, we're just given a bunch of data. We're not given an equation. So what we're going to do is we're going to take our data and see, okay, can we come up with a reasonable equation based on this data? Okay. Usually, a good way to do this visually is by making what's called a scatter plot, where we just take our data, plot all of it onto a graph, and see if there's any kind of relationship that we can deduce from that. Okay. So a scatter plot is a graph showing all of our data points. Okay. So for example, let's look at this data that they have here, where X is our year, Y is the number of users. Okay. And they have in 2000, this company had 0.5 users. The users is, I'm trying to see. Yeah, the users is in millions. So it's 500,000 users. Okay. 2002, they have 20 million users. 2003, they have 33 million users. 2004, they have 47 million users. Okay. So what we want to do is we just want to take these numbers and make a graph out of them. Okay. Um, so obviously we're not going to want to use our 1, 2, 3, etc. scale because these numbers are way too big for that. So our X, that'll go along here. And our Y will go along here. Okay. So we'll have our 2000, 2002, 2003, 2004. Okay. Maybe if you like, you can move these over and throw a 2001 in there as well. Okay. Even though we don't have a data point for that. And then say we got 50 up here. 30, 40, 20, 10. Okay. So at 2000, we have only a half. So it's pretty close to a 0 based on our scale here. 2001, we don't have a data point. 2000, we are at 20. 2003, we're at 33. 2004, we're at 47. Okay. So we just plot the data points, and the purpose of this is to say, okay, is there a reasonably linear relationship between these numbers? And it looks like yes. Like it looks like we could draw a straight line straight through that. If you can imagine, like at 2001, if it's right here, then you got a perfectly straight line almost. So it's looking like, okay, there's probably a linear relationship here. And that's all this is used for. If we want to actually calculate the equation for that linear relationship, we're going to need some different methods to do that. But what this allows us to do is to predict trends, because now we can say, okay, in 2005, it's probably going to be close to 60 million users, right? And then when we get the equation, we'll be able to do that more precisely. This is just a way to visualize it first. Okay. I think we can do this in Excel. Let me pull that up. Okay, so I got Excel pulled up here. Let's go ahead and put our data in. So we have 2000 and 0.5, 2002 and 20, 2003, 30, I think it was 33, and 2004 and 47. I think good, yep. All right, so once we have our data here, you want to go to Insert, and then we're going to look at, I think we might need to highlight it. Yep. So you want to highlight it first, or you probably can highlight it after. And then you want to go to this part right here, and you want to go to the first one, the scatter plot here, and it makes a nice little graph for us. Okay. And we can see very easily, that it looks like there's going to be a linear relationship here. Okay. So a scatter plot shows the direction of a relationship between the variables. So it shows the direction of a relationship between the variables as well as the strength of the relationship. Okay. So it shows it in the sense that it's basically like a good jumping off point. If you see that there looks like there's going to be a relationship, then you can start getting into the nitty gritty of the math and figuring out exactly how strong the relationship is, which we're going to do in 12.3. But with the scatter plots themselves, we can usually get a decent idea. For example, if it looks like this, okay, then this is a linear relationship. It's a little different than the ones we saw before, right? This one had an upwards trajectory. This one has a downwards trajectory. This is what we would call a negative relationship, meaning as one of the variables increases, the other one decreases. Later, we would say that they're negatively correlated, whereas these ones are positively correlated, or they have a positive relationship. When one increases, the other increases. So that's what we mean by direction, whether it's heading upwards or heading downwards. The strength of the relationship is how close to linear is it? Is it something like this, but then there's also this and this and this. So it's like, okay, can kind of see a line in here, like, maybe like going through here, and that line's pretty close to a lot of those data points, but it's really far away from this one and this one. So maybe there's a relationship here, but it's probably a pretty weak one if there is. Okay. Or maybe we just have points that are seemingly all over the place. Okay. Where it's just seemingly random. Because then we go, okay, it doesn't look like there's any kind of linear relationship at all. So there's not really much to do there. Maybe then there's something like this, where it's like same idea, like maybe we could fit a line down here, or maybe like up here. And then it's pretty close to all the points, and maybe it's decently strong. It's not going to be the strongest, but maybe it could work, right? Like this would be a good example of where it's like, okay, now we should maybe try out the math and try to figure out what that equation is and see how strong it really is. Okay. So these are the ideas we're going to be working with. Let's jump into 12.3 now so we can actually start calculating some of this. How do we actually do these calculations? How do we actually read the numbers? Okay. We're typically looking for the best fit line. Okay. Which is called the line of best fit, or the least squares line, which is derived from the method that's used to come up with the line. So we're looking for the line that best fits through this data, meaning that it is the closest it could possibly be to every point. Okay. Um, so let's see. We use what is called the least squares regression line. Okay. So let's look at um let's look at this diagram in the book. Let me pull it up. I guess I'll copy and paste it. All right. So let's consider this diagram here. Okay, and we'll consider this line that they made through it. And what we want to determine is this the best fit line? Okay. So some things we might notice here. A point on the line is referred to as x comma y hat. Okay. Whereas a regular data point is referred to as x comma y. They use the zeros here just to represent that this is the first data point. Okay. The y hat read y hat is the estimated value of y using the regression line. Okay. So in statistics, we always use hat to represent an estimate. Okay. So this is saying that if we were just using the line, it estimates that the y would be at this point. Of course, we already know that it's not because we have the data. We have it's right here. So we want to take that into account and we want to say, okay, well, we know what the actual data point is versus what this line is predicting the data point is. And the distance, the difference between those two, we call epsilon, which is the error. Okay. So the error or the residual, it's another word for it, is the distance between the actual data value and the predicted data value from that line. Okay. And we call that epsilon. So the equation here would be epsilon. Epsilon just looks like an E basically, just a little more squiggly basically. This is usually how I write them. Epsilon is the absolute value of your y hat minus your y. Okay. The absolute value is just there so that you can either do y hat minus y or y minus y hat. And the absolute value just makes it positive. Okay. Technically, this should have an absolute value around it also. But that's not as important. It's just whatever the difference is here, and then you make it positive. So the absolute value is just there so that you can do the subtraction in either order, and you'll get the same thing. Okay. So it's important to note this isn't an error in the sense of like a mistake, right? We're intentionally using this line, so it's not mistaken. It's just how far is the true value away from the predicted value. Okay. Okay. So for this one, how many data points do we have? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So that 0 is indicating the error for the first value, okay? If we were to take all of them and square them, so it kind of um, it kind of changes the notation. In this diagram, it's calling it 0, but then when it gets to this equation, it starts calling the first one 1, and it goes 1 through 11 instead of 0 through 10, like they kind of should have with how they're counting here. So we'll switch, and now we'll call that epsilon 1. If we take all of the data, so epsilon 1, epsilon 2, etc., and then we square all of them, well, we square all of them first and then we add them, okay? And we do that all the way up to epsilon 11, and we square it, which we could write using our previous sigma notation as this, okay? This is called the sum of squared errors, okay, or SSE, or sometimes it's called the residual sum of squares, so RSS. And this happens to be one of the most important things for regression. We look at the errors and we square all of them. So that would be like this distance squared this distance, the distance between this point and the point on the line, square that. The distance between this one and that blue dot, this line and this blue dot, etc. You just go through and you find all of the distances, you square them, and then you add them together. Whatever that number is, that's called the sum of squared errors. Okay. So using calculus, you can determine the values A and B, remember from this equation, that make, it's actually y hat, I guess, because we're using, because on this line we're calling things y hat, that make the SSE minimized. Okay. So that's our goal. We want to make the error minimized, right? Because we want to have as little error as possible. We want to have as little distance between the predicted value and the true value. I did that backwards. The predicted value and the true value as possible. Okay. We want to minimize that error, and we need calculus in order to do that. So we're just going to write out what it turns out to be. Okay. When you do this, we find that the line of best fit, y hat equals a plus bx, is when a is equal to y bar minus bx bar. So remember, y bar and x bar are the means of x and the mean of y. So let me write that as a note over here. Y bar equals mean of y. Okay. And b is equal to the sum of x minus x bar and y minus y bars divided by the sum of x minus x bar squared. So that one's a little more complicated. Luckily, we'll be able to do most of this in Excel anyway. The bottom one, you might notice that's almost the standard deviation. It's pretty close. The only difference is we're not dividing by n minus 1. Okay. So alternatively, B can be written as B equals R times S sub Y divided by S sub X, where SY is the standard deviation of the Y values. SX would be the standard deviation of the X values, of course. And R is the correlation coefficient, which is going to be discussed in the next chapter, next section. Okay. R is very important. R is actually going to be the number that tells us the strength of the relationship. Okay. So this process of fitting the best fit line is called linear regression. Okay. And the best fit line is called the least squares regression line. Okay. All right. Let's see. Let's do an example with our previous data here. Okay, let me grab this. And we'll use Excel to do a lot of the more tedious calculations here. Okay. So let's look at what numbers we're going to need. We're going to need the mean of Y. We're going to need the mean of X. So let's go ahead and just find those. Okay. So I'll just do it down here, I guess. Mean X, mean Y. So we're going to go to formulas, stats, average. The X's are these ones. Okay, so we get 2000.25. The mean of the Y's, we got 25.125. And then we're going to need to calculate what B is. Okay, so that's going to be a little bit more of a challenge, of course. There are formulas just to calculate the correlation coefficient itself. I think that's this right here. Yeah, it returns the correlation coefficient between the two data sets. So let's just go ahead and do it that way. So we're just going to use this definition. Okay. So we didn't actually talk about what R is yet, but we'll just go ahead and use it for this equation right here anyway. So we got the correlation coefficient. So let's see which one should be which. Does it tell us? I don't think so. So that's this one, that's this one. So we get 0.9956. I don't think the order matters. I'm just trying to make sure. Let's do it the opposite way. Let's make array 1 this and array 2 this. Yeah, and it's the same thing. Okay, so the order doesn't actually matter. So then we need S sub x and S sub y, the standard deviations, and then we'll have all the parts that we need here. Standard deviation, this is the sample standard deviation of x would be these ones, and then y would be these ones. Okay, so we got everything we need now. So b is going to be r, which is A33 times B33 divided by C, nope, wrong way, C33 divided by B33, right? SY divided by SX. So that's our B, and then A is equal to Y bar, which is B28 minus B, which is A36 times X bar, which is A28. Okay. Does that make sense? I don't think it does. So something must be wrong here. Mean. B makes sense. I think that one's fine. Let me think here. I think this should have calculated it correctly, but let me make sure and put this in parentheses. A28 is the mean of X. Okay, I mean, maybe that is right. It just seems like a very low number. I'm not sure. But anyway, what this is saying is that then the best fit line for these numbers are negative. It would be Y bar equals negative 23,058 plus 11 point, let's say 53 X. And then what we would do is we'd use this to make predictions. So we'd say when X is, I think this does make sense actually. When X is 2000, for example. So let's make a chart for X and Y bar. Okay. If X is 2000, we know Y, the actual Y was 0.5. And this should be very good at predicting because R is, well, it was like 0.99, which we'll see soon means that it's almost a perfect relationship. So this should be really close to 0.5. 11.53 times 2000 minus 23,058 gives us 2. Okay, so it's really close. It's not exact, it's not 0.5, but it's really close to it still. If we use 2002 times 11.53, and then we subtract 23,058, we get 25.06, which is close to our actual 20. So, you know, it's far off, but it's getting within a reasonable range of the actual values. So what we'd want to use this for is making predictions like, okay, what's going to happen in 2005, right? And then we can just put 2005 into our equation, subtract 23058, and we get 59.65, which seems reasonable based on the trends here, right? And this is, I mean, this is what companies do. This is how they predict things that are going to happen. Maybe not necessarily with a linear relationship, but they look at previous data and look at what the relationship is and use that to predict what the future is going to be like. Okay. So I think that there is a built-in correlation function here. Let me see. I'm pretty sure I have it somewhere. Let me look for it real quick. Okay, so there's not a built-in linear regression function. There is like an add-on that you can add into it, which I've used before. So the best way seems to be just doing it the way we did, where we just use the functions to calculate everything individually. Okay. I think we'll end it there today. So next time what we're going to do is we're going to look more at what that R is. Because I said this R value shows that there's a very strong relationship. What exactly does that mean? So we'll look at that, and then we'll just continue on from there. So thanks for watching today, and hope you have a good day.